What else can we do with the idea of a first order process? The half-life. How long does it take for the amount of a reactant to decrease to half of its original value? There is a formula for this, and I just like to show you first of all where the formula comes from. If we go back to our first order integrated rate law that looks like this, then we can start rearranging things. It's going to look a little bit like what we were doing earlier. It's just the opposite direction at the moment. And because of the rules of logarithms, this means the logarithm of x over the original value. And if I'm trying to do a half-life, then I'm saying that the amount left is half of what this original was. So this would end up with the natural log of 1/2 equals minus kt. And when I did that, I'd end up with a negative number here and that negative, so those will cancel. Since I have said that this is for 1/2, I'll start labeling this as the half-life, the time. And then I can just cancel out the minus signs and rearrange it, and I will get the formula that you see on the page. So that's where it comes from. And now we're going to do a little puzzle with it. So radioactive decay is a first order process. So now this is more of a physics problem, but it still responds to the same sort of kinetics analysis that we do on our chemistry problems. So here's a radium dial on a wristwatch, and it glows from a decay process. If the half-life is 1,600 years, what's the rate constant? Okay, so they're going to give me this number, and then they're going to ask for the K. Well, I can just rearrange the formula. K equals 0.693 and divide it by the half-life. They have told me the half-life, so I will put the number in. 1,600 years. And when I run this through the calculator, I'll get a small number because of how many years they were talking about. And then this would be per year in first years. Now there's a question. 100 years after the dial is constructed, what percentage of radium is left? So now I want to do how much is there when I knew the original amount. This is a first order decay equation. And you could get this just as easily from our process up here if you needed to, because this is expressed without logarithms. This has e in it. I got this from here, essentially. What I did is say, I want to undo logarithm. Well, the way to undo logarithm is to use it as an exponent of e. When I do that, the e and the logarithm cancel, and I would get x over xo, and then e to the minus kt. Anyway, I've got this. What percentage of radium is left? I will rearrange it so that it looks like this, because this would give me what's left over the original, right? So this should help me figure this out, and this would leave it as e to the minus kt. Well, I know what k is. I just got through figuring it out, and they told me the amount of time, 100 years. So this is really going to be e to the negative 4.33. Okay, I have 100 years. The years are going to cancel out. This is going to become times 10 to the minus 2. It's now a pure number, which is good because I have to have a pure number to use it as an exponent. And when I use my calculator, I get the answer of 0.958. So after 100 years, you would think, wow, that's a long time for a watch. Maybe it wouldn't be any good. Maybe the dial wouldn't glow anymore. But guess what? Almost 96% of the radium is still left. So you're not really going to notice any diminishment in how much it glows. Since we just found out that was pretty spectacular, then the next question, how long will it take for 99% of the radium to decay? Well, I don't have a number for decay. What I have is a number for how much is left. So if it's 99% decayed, that means 1% is left. So what I'm going to do is say that this A over A original is going to be 0.01. That's 1%. And that's going to be equal to the E to the minus kt. I know what k is. I need to get t. This is up in an exponent. The way to get that out, take a logarithm. So I'll take the natural log of 0.01. The natural log of this will wipe that out, and I'll get the minus kt here. So I will put the k in, find out what the t is. Using my calculator, it's the natural log of 0.01 over the negative 4.33 times 10 to the minus 4th. This turns out to be a negative number. The negatives will cancel, and you'll end up getting 1.06 times 10 to the 4th years. That's 10,000 years. But the dial will still have a little glow.